Hi, back again for part two. So, the heat flow that I was talking about before, and that you've hopefully have done the calorimetry experiment for, that heat flow was between an object and its surroundings, a piece of metal and the water being the surroundings. But we want to start talking a little bit about the heat for a reaction. And the heat for a reaction really has a special name, and it's called the heat content or the chemical energy. And it has a fancy name, enthalpy. So when we look at the heat flow in a chemical reaction, we look at the difference in the enthalpy between the reactants and the products. So enthalpy, in short, is a type of chemical energy, and it is the heat content. So we can say that the change in the energy, the enthalpy, as a reaction proceeds from reactant to product, is equal to the enthalpy of the products minus the enthalpy of the reactants. And so we can also say that for a reaction, we can say that the Q of a reaction is also equal to the delta H. So in the second lab for this week, the additivity of heats of reaction, Hess's law, this is exactly what you'll be proving, that if you can find the delta H for a series of reactions, then the delta H for the one summative reaction should be equal to the sum of the two delta H's. That's a lot until you've actually looked at the lab. So if I were to, as I use these examples before, take the solid water, the ice, and melt it, I have to add energy, so the Q would be positive. The delta H would also be positive. It's endothermic. And then conversely, if I took methane, burned it in oxygen, I'm going to release energy in that process. The Q would calculate out to be a negative value. Therefore, the delta H is also negative, and this would be an exothermic process. So, again, describing the difference between exo and endothermic. So here's an example of an endothermic process. If you take those cold packs that you use, athletes use if they have an injury, a minor injury, and they have some swelling, and coach will break the packet open and bend it to activate the two different pockets. One pocket has ammonium nitrate, the other pocket has water. And when those two come in contact with each other, ammonium ions and nitrate ions are released. In that process, energy is absorbed from the surroundings, making the delta H a positive value, endothermic absorption of energy. So what would that look like in a chemical equation? It would look like this. This is what we call a thermochemical equation, where I put the energy term right in the balanced equation. Talk about lots of balanced equations in Chem 1, but you don't typically talk about energy until you need to talk about it, but it is always present as part of a chemical reaction. So as I pull energy in from the water to split apart the ions, then the pack, which is the water surrounding it, would cool. So that's just a nice practical example of an endothermic dissolving process. So there are some important rules for thermochemical equations, and these rules some of them are illustrated in a couple of the videos that I did that are also listed here in this folder. So these are the three main ones that are very important. The magnitude of delta H is proportional to the amount of reactant and product. Number two, delta H is equal and opposite when the equation is reversed. And the delta H for a series of reactions is the sum of the series. Hess's law. That's the second lab for this week, which is a really nice illustration of it. So for the first law, the magnitude of delta H is proportional to the amount. So you're going to use some of your dimensional analysis to do this. So let's say, as an example, I had 10 grams of water and I wanted to find out how much energy would be needed to evaporate it, or to decompose it into hydrogen and oxygen gas. So I know for a fact, so this would be given information, that 571.6 kilojoules of energy are needed for this reaction. So this reaction is for every 2 moles of liquid water. So using my dimensional analysis that I know from Chem 1, I'd start out with 10 grams of water. I know that I would convert to moles by using this conversion factor here. That's just the molar mass of H2O. And that's taking 2 hydrogens and 1 oxygen, adding up their atomic masses and getting the molar mass. And then I would use this fact that I'm pulling from the thermochemical equation as my last conversion factor. So I would plug into my calculator 10. I would divide by 18.02. I would multiply by 571.6 and divide by 2. And that would give me my final answer. And all of my units would cancel. Mole would cancel with mole. Gram would cancel with gram of H2O. And the final unit that would be left would be in kilojoules. Sorry, I did not do that final calculation, but I'm sure you can plug those numbers into your calculator. Okay, so then the second rule, delta H is equal and opposite when the equation is reversed. So if I take this equation that's given here and I reverse it, then look what happens to the delta H. It becomes a negative 571.6. And that's always true for the delta H when you reverse the direction of the equation. And so this is the one that's a little tricky that you really need to understand. There is a video on it in the folder. So if I have these two equations that add up to this one final equation, this is called a reaction mechanism. Many reactions don't occur in one step. It takes a couple of steps for the reaction to occur. And if I know the delta H for each of the individual steps, so this would be my first step, this would be my second step. And so if I know those values and these two equations are summed up to this one final equation, then the final delta H of this third reaction would be equal to the sum of the two above, and keeping in mind that you have to be careful of your signs. So if I look here and I see that that my first one, my second one, I would have to change the direction of it. So if I change the direction of this reaction, I change the sign to positive, and then when I can add these two equations up, I should end up with that third equation. So let me show you how that flips around. So if I take this second equation here and I turn it around to CO2, I literally just flip it around, and when I do that, I have 2CO plus O2, and now my delta H is no longer that negative value that it was originally. it now becomes the positive 566. Okay, so it was originally negative. Sorry about that. Okay, so now what I do is I want to see what I need down here. So what I can see is that I need to get rid of the CO2s. So what I see here is that I have, because the CO2s don't exist in this final reaction. So I have one CO2 here and I have two here. So what I have to do at this point is I have to divide everything through by 2. So I'm trying to end up with only that third equation. And I make these manipulations according to my rules. So now what I see is that, first of all, I'm going to get rid of this reaction here. I don't need it now because I've flipped it around. So now if I divide it by 2, I have one CO2 here and one here, and it crosses out. And then what I can see is that I have a half of an O2 here, and I have a whole O2 here, so that would leave me with a half here. Okay, so now what I'm going to do, glad I have colored pens here. Now what I'm going to do is I'm just going to pull down whatever's left. The carbon is left. There it is in my final. There's half of an oxygen left. There it is in my final equation. And then there's one CO left. I have 2 halves, which is just one CO. So there I did it. I managed to manipulate these 2 equations, 1, 2, in order to become ultimately this third equation. So when I did it, don't forget here that since I divided everything by 2, according to that first rule, I've got to divide that by 2. So now my final answer for the delta H of this third reaction is going to be a negative 393.5 and a positive 566 divided by 2, and that would give me my answer for the delta H right there. Okay, I'm going to stop there and then I'll come back.